Hello friends, I welcome you in lecture number 1 on singularities and zeros of analytic functions. So first we will discuss what is singularities, and then in upcoming lectures we will discuss zeros of analytic functions, and then we will discuss what is the relationship between singularities and zeros of analytic functions. So first we start with the definition of singularity or singular point. So suppose z0 is any point in the complex plane, then this point z0 is called a singular point of a function f if function is not analytic at z0 but it is analytic at some point in each neighborhood of z0. We understand with this figure. Suppose z0 is somewhere there in the complex plane, and this z0 is called singular point of function f of z if function is not analytic at z0, but if we consider any neighborhood of z0, then function must be analytic at some point in that neighborhood. Suppose I consider this point, and if function is analytic at this point which is inside the neighborhood of z0, then this z0 is called singular point. Now if I consider another neighborhood of z0, then also I must have at least one point in that neighborhood also, such that function is analytic at that point. So z0 is singularity of a function f of z if function is not analytic at z0 but function is analytic at some point in every neighborhood of z0. For example, if we consider this function, say f of z equal to 1 by z, we understand here. Suppose we consider this function f of z equal to 1 by z, then we know that this is not analytic at z equal to 0. So function is not analytic at z equal to 0. So there are chances that z equal to 0 is singular point of this function. So we have to check whether function is analytic at some point in any neighborhood of z0. Suppose I consider this neighborhood of z0, then because function is not analytic at z equal to 0 only, we can see that function is analytic at all other points which are in the neighborhood of z equal to 0. If I consider this point, then I can always find out some neighborhood of this point such that function is differentiable at every point in that neighborhood. That means function is analytic at this point. Similarly, function is analytic at all these points. We require at least one point. In this way, if we consider any neighborhood of z0, however small, we will always have at least one point in that neighborhood such that our function is analytic at that point. But if we consider this function square of absolute value of z, then we know that this function is nowhere analytic. There is no point at which function is analytic, or we can say that every point of the complex plane, if we consider any point in the complex plane, then this function is not analytic at that point. So there are no chances that if we consider neighborhood of this point, then because function is nowhere analytic, it is not analytic at any point in this neighborhood. So this means this function has no singular points. So if our function is nowhere analytic, it will have no singular points. We consider another function. Suppose we consider f of z equal to z plus 1 divided by z square times z square plus 1. Then this is rational function. If we want to decide singular points of this rational function, we can put denominator equal to 0, because function is not analytic at those points where denominator becomes 0. So this is z equal to 0, z square is minus 1, that is I square, that means z equal to I minus I. So these are the 3 points at which function is not analytic. So there are chances that these points might be singularities of this function. So z equal to 0 is somewhere here. Suppose this distance is 1, then this point is I and this is minus I. So if we want to check whether z equal to 0 is singularity of f of z or not, then by definition we have to check that function is analytic at some point in any neighborhood of z0. Suppose I consider absolute value of z equal to 1. If I consider this neighborhood, radius is 1. Okay, so I consider this neighborhood of z equal to 0. Absolute value of z is less than 1. So function is not analytic at these 3 points only. But if I consider this point, then if I consider this neighborhood of this point, then we can see function is analytic at this point. Function is analytic at a point if there exists a neighborhood of that point such that function is differentiable at every point in that neighborhood. So we can always find out at least one point in any neighborhood of 0 such that function is analytic at that point. So 0 is singularity of f of z. Similarly, we can consider any neighborhood of this point z equal to I, and we will always find at least one point in this neighborhood such that function is analytic at that point. So function is analytic at this point, this point. There are infinite number of points, and similarly we can check by considering any neighborhood of z equal to minus I. So these 3 are nothing but singularities of this function f of z equal to z plus 1 over z square divided into z square plus 1. We consider one more example. Suppose I consider f of z equal to 1 over sine pi by z. Then we know that this 1 is analytic everywhere, and sine pi by z is not analytic if z equal to 0, because we have 1 pi by z here, and because we have division of these two functions, f of z is not analytic at those points at which value of sine pi by z is 0. And as we know, sine pi by z is 0 if pi by z is multiple of pi, n belongs to z, and we will not consider n equal to 0. And from this we can cancel out pi, and z is 1 by n. N is not equal to 0, so there is no problem. So z is 1 by n and z equal to 0. So all these are points at which f of z is not analytic. So z equal to 0 here, 1 by n, suppose we consider this as 1. So for n equal to 1, z is 1. For n equal to 1 by 2, z is 1 by, for n equal to 2, z is 1 by 2. For n equal to 3, z will be 1 by 3. So somewhere here say, then 1 by 4 and so on. So these are the points at which function is not analytic. Z equal to 1 by n, and of course z equal to 0. So function is not analytic at all these points. Now first we check for z equal to 0. So if z equal to 0 is singularity of f of z, then we have to check that we can find out at least one point in neighborhood of 0 at which function is analytic. So if we consider any neighborhood of z equal to 0, then we know that function is not analytic at these points z equal to 0 and z equal to 1 by n. But if we consider this point, then function is analytic at this point. We can always find out at least one neighborhood of this point at which function is differentiable. So for z equal to 0, we are always able to find out at least one point in every neighborhood of z equal to 0 at which function is analytic. Therefore z equal to 0 is singular point of f of z. Similarly, we can check for this point also, z equal to 1 by 2. Here also same logic. If we consider any neighborhood of z equal to 1 by 2, we will always find out at least one point in that neighborhood at which function is analytic. So all these z equal to 1 by n, z equal to 0, all these are nothing but singularities of given function, which is 1 over sin pi over z. So this is meaning of singularities. So again we repeat, a singular point z0, a point z0 of a function f. Just a minute, this is definition of isolated singular point, we will come it later. Okay, a point z0 is called a singularity or singular point of a function f if f is not analytic at that point, but f is analytic at some point in each neighborhood of z0. So as we discussed, z equal to 0 is singularity of f of z equal to 1 by z. The function f of z equal to mod z square has no singular points since it is nowhere analytic. Now this is another definition. Here we want to define isolated singular point. So for that our point must be singular point. So when a singular point is called isolated singular point, so definition, a singular point z0 of a function f is called an isolated singular point if there exists a deleted neighborhood of that point throughout which f is analytic. So that means if z0 is singular point, suppose z0 is singular point, and if we can find out a circle with radius say epsilon and center z0, and if we consider this set of points, absolute value of z minus z0 less than epsilon, and we do not consider center of the circle, so we take this condition, absolute value of z minus z0 is greater than 0. So if there exists a deleted neighborhood, so here deleted neighborhood means set of all points inside this circle without considering center of the circle. So these are the points at which we have to see whether our function is analytic or not. So if there this set is known as deleted neighborhood of z0. So if our function is analytic at every point in this deleted neighborhood of z0, then this singular point z0 is called isolated singular point. For example, we have seen that this f of z equal to 1 by z has z equal to 0 as singular point. So z equal to 0 is singular point of this function, and as we know this function is not analytic at this point only, z equal to 0. So if we consider any neighborhood of z equal to 0 excluding z equal to 0, suppose this is deleted neighborhood of z equal to 0, then because function is not analytic at z equal to 0 only, it is analytic at every point in this deleted neighborhood except z equal to 0. So that means z equal to 0 is isolated singular point of f of z equal to 1 by z. Similarly, suppose we consider that function again, z plus 1 over z square into z square plus 1. So as we discussed, these are the singularities of this function, z equal to 0, I and minus I. So all these are isolated singular points or not. So for that we have to find out their deleted neighborhoods in which function is analytic. Now this function is not analytic at these points only. So suppose I consider this neighborhood of z equal to 0. First I consider this neighborhood. So this distance is 1, so that means 0 less than absolute value of z minus 0 less than 1. This is the deleted neighborhood of z equal to 0, which does not contain z equal to 0 and these points also, and function is not analytic at these points only. So we can say that function is analytic in this deleted neighborhood of z equal to 0. Therefore z equal to 0 is isolated singular point. Similarly, if we want to show that this point I is isolated singular point, then we have to find out deleted neighborhood of this point z equal to I such that function is analytic in that deleted neighborhood. So for that what we can do, we can consider the radius as distance of I from the point, from the nearest singular point, which is 0. So if we consider distance between I and 0, which is 1, so we will consider the circle of radius 1 with center I, so that will pass through 2I. Okay, so if we consider the circle with center I and radius, so we will obtain this circle. Okay, so center of this circle is I, radius is 1, so it will not include this point and this point also, and if we exclude I from this, then this is the deleted neighborhood of the point z equal to I, radius is 1, and this deleted neighborhood does not contain z equal to 0 and minus I, and also z equal to I is excluded. So function is analytic in this deleted neighborhood, therefore z equal to I is also isolated singular point of this function. Similarly, if we consider this point z equal to minus I, then we know that this distance is 1. So if we consider circle with center I and radius 1, then our function is analytic at every point in this deleted neighborhood except z equal to minus I. So this is the deleted neighborhood of z equal to minus I, which is absolute value of z plus I less than 1, and function is analytic in this deleted neighborhood. Therefore this z equal to minus I is also isolated singular point. So this is the definition of isolated singular point. We can again discuss this function for isolated singular points. We have seen that z equal to 1 by n and 0 are singularities of this function. So we check whether they are going to be isolated singularities or not. So for example, suppose this is xy plane, suppose this is z equal to 0, this is 1, or this is 1 by 2, 1 by 3 and so on. We can have 1 by 4 also. So first we discuss for z equal to 0. Z equal to 0 is singularity of this function. Now we check whether we can find out deleted neighborhood of z equal to 0 in which our function is analytic. So suppose I consider circle with center z equal to 0 and any positive radius. Suppose I consider this circle. So this is the circle with center z equal to 0 and radius any epsilon. So now if our function has isolated singularity at z equal to 0, then we must find out at least one neighborhood of z equal to 0 such that function is analytic at every point in that neighborhood. Now this z equal to 1 by n are the points at which function is not analytic. So you can visualize this neighborhood here. Here we have z equal to 0. Now if we consider this part of the neighborhood, then this part will always contain at least one point of this form, 1 by n. So we are not having isolated singularity at z equal to 0, because if we consider any deleted neighborhood of z equal to 0, it will always contain this portion of x-axis, and this portion is to the left side of 1. It is in between 0 and 1. So there will always be at least one point of this type 1 by n at which function is not analytic. So it is not possible to find out any deleted neighborhood of z equal to 0 which does not contain these singularities z equal to 1 by n. So that means z equal to 0 is not isolated singularity of this function, because there does not exist any deleted neighborhood of z equal to 0 such that function is analytic throughout that neighborhood. So z equal to 0 is a singularity of this function, but it is not isolated singular point of this function. Now we check at all these points. Suppose we want to check at 1 by 3, then we have to find out deleted neighborhood of z0 equal to 1 by 3 such that function is analytic throughout that deleted neighborhood. So that we can do easily, because if we observe, this is the nearest point 1 by 4 at which this function is not analytic. So if we consider circle which has this 1 by 4 is on the boundary of that circle, then our function will be analytic at every point in the deleted neighborhood of this z equal to 1 by 3. So we can find out deleted neighborhood of z equal to 1 by 3 such that function is analytic at every point in that deleted neighborhood, and this epsilon is nothing but distance between these two, 1 by 3 and 1 by 4, distance between the point 1 by 4 and 1 by 3. So we will always consider this radius as the distance of center from the nearest point at which function is not analytic. Similarly, if we consider z equal to 1 by 2, then this 1 by 3 is the nearest point. So we can consider this circle, and if we consider set of all points inside this deleted neighborhood, then function is analytic throughout that deleted neighborhood. So therefore for any point z equal to 1 by n, we can always find out at least one deleted neighborhood of this point such that function is analytic throughout that deleted neighborhood. Okay, we can always have this type of deleted neighborhood such that function is analytic throughout this deleted neighborhood. Radius of this deleted neighborhood will be distance of the point 1 by n from the point nearest point at which function is not analytic. So this is meaning of isolated singular point. So isolated singular points means it is a singular point of a function f for which there exists a deleted neighborhood given by 0 less than absolute value of z minus z0 less than epsilon, such that our function is analytic throughout this deleted neighborhood. Or we can always find out at least one deleted neighborhood of z0 which does not contain any other singularity of given function. So as we discussed, this function z plus 1 over z square times z square plus 1 has three isolated singularities 0, I and minus I. This function also we discussed 1 over sin pi by z has an infinite number of isolated singularities given by z equal to 1 by n, where n is different from 0, and of course here n is integer. Instead of n we can write z. N will also work, but n belongs to z is in general. And as we discussed, point z equal to 0 is singularity of f of z, but it is not isolated because every deleted neighborhood of 0 contains singularities of the function. Similarly, we can talk about this function f of z equal to tan z. This we can rewrite as sin z over cos z. So these two are entire functions, analytic everywhere. So tan z is not analytic at those points at which cos z is 0, and cos z is 0 at all these points, plus or minus odd multiples of pi by 2, odd integer multiples of pi by 2, and this is 5 pi by 2. So this function is not analytic at these points, pi by 2, 3 pi by 2, 5 pi by 2, or minus pi by 2, minus 3 pi by 2. Okay, so at these points tan z is not analytic. Okay, suppose this distance is pi by 2, so this is pi, this is 3 pi by 2. Similarly, this is minus pi by 2, minus 3 pi by 2, and so on. This is somewhere here we will have minus pi. So all these are points at which our function is not analytic. But we can see, if we consider a deleted neighborhood of all these points, here suppose we want to talk about pi by 2, then the distance of pi by 2 from this point pi, not pi, from 3 pi by 2. So that is 3 pi by 2, that is pi, distance is pi. So distance of pi by 2 from the nearest singularity is pi, same thing here. So if we consider circle with center pi by 2 and radius pi, approximately we can see suppose this is passing through minus pi by 2 and here from 3 pi by 2. So if I consider this circle with radius pi and center pi by 2, then this is nothing but deleted neighborhood of pi by 2 with radius pi and center pi by 2. So this deleted neighborhood does not contain any other singularity of the function. So function is analytic at every point in this deleted neighborhood except center, that is z equal to pi by 2. So that means z equal to pi by 2 is isolated singular point of tan z. Similarly, we can check at 3 pi by 2. Again we will consider deleted neighborhood of 3 pi by 2. So again here also radius is going to be pi, because distance between pi by 2 and 3 pi by 2 is pi. So if we consider this deleted neighborhood, then function is analytic at every point in this deleted neighborhood. Therefore z equal to 3 pi by 2 is isolated singularity of this function. So similarly all these are going to be isolated singularities. The function tan z has isolated singularities at plus or minus pi by 2, plus or minus 3 pi by 2. In general we can write that plus or minus 2n minus 1 pi by 2 n belongs to n. So in this way we can decide the isolated singularities of the given function. So this is all about today's session. In the next lecture we will discuss about classification of isolated singularities. I hope you like this lecture. Thank you very much.